This is Unit 10, your very last unit for the year. We're going to study thermochemistry, which combines the energy and chemistry. So we can talk about what actually happens in a reaction. Okay, I'd like to get rid of this. There we go. All done. You guys ready? Mrs. Uy is here with me, so I'll let her say hi.
Hi guys, how are you? I hope you're ready to learn thermochemistry.
All right, here we go. In this podcast, 10.1, we're just going to talk about heat. And it's pretty simple. We're going to define what is the system and what is the surroundings. We'll classify an energy change as endothermic or exothermic. And as we normally do, Mrs. Uy, we've got to talk about units.
If it's unit, what is it all about? It's calculation.
Calculations again.
Yeah.
Yep. And then we'll be calculating the amount of heat that is transferred during a physical change. And then we'll also show them how to do it for a chemical change.
Okay. Interesting.
Here we go. Let's get started. You've been ready. First of all, let's talk about what thermochemistry is. It's the study of energy changes that occur when we have a chemical reaction or a change in the state of a substance, like solid, liquid, or gas, or changing solid to liquid. So that doesn't change what it is, but it certainly involves some energy. So kinetic energy we talked about in the last unit. Do you remember that one?
I think so. What is kinetic energy? You still remember?
I hope I do.
All right. Kinetic energy is the energy of motion.
So we've got to have things moving. And remember, temperature is the measure of the average kinetic energy of a substance. So those two are closely related, but heat is not the same thing as temperature. So we want to make sure that everybody understands what we mean by heat. Potential energy is stored energy. So in chemistry, the energy is stored between chemical bonds. If we break a bond, we release the energy. And when we form a bond, we store the energy. It takes energy to form a bond, and we release the energy when we break the bond. Yeah. So that's why when you eat your food, it gives you energy, because you break the bonds between the glucose molecules. The more bonds there are, the more bonds, the more energy. And what that refers to is that if we have a single bond, that's going to be less energy than a double bond, or like this one here, I think is pretty cool. Yeah, triple bond, like in nitrogen. This is a bond in trinitrotoluene, or TNT. That's what they used to make dynamite.
Wow.
Yeah, that's a lot of energy.
Yeah, that's a lot of energy.
Right. All right, so then we're going to look at energy that transfers from one object to another due to a difference in temperature. It's called heat, and its symbol is Q. So we will use a lowercase q for heat. Sometimes you'll see in a book that they use capital Q.
Is that the same?
It will be the same, but I think chemists always prefer to use the lowercase q.
So we're going to use that.
Yeah, we're going to be consistent every time. But if you see someone else use a capital Q, don't let that stop you from getting the question right.
Yes.
Okay, well, let's talk about heat transfer. So I want you to do an experiment with me real quick, Mrs. Louis. Okay, it's pretty simple. Put one hand on your desk. So I'm going to draw the desk. Mrs. Louis' hand is at the top of her desk. All right? Okay, so touching the desk, right? You know, your other hand has to reach down here and touch the metal leg of the desk.
My other hand?
Yes, your other hand. Which hand feels more heat?
The one at top?
The one on the wooden part of the desk?
Yeah.
And the hand touching the metal, how's that feel?
Well, right now it's cold.
It feels cold to you?
Yes.
Okay, understand this then. The desks have been in your classroom all day long, right?
Yes.
So they have been in the same temperature all day long. So the temperature of the desk is the same on top as it is down here on the leg. They're the same temperature.
Yes.
Why does the metal leg feel colder? Any ideas?
Is it because...
Which way does heat move? Is it going to move from the desk to your body or from your body to the desk?
From the desk to my body.
Probably,
right?
Probably not, because the desk is the temperature of the air in the room. And we'll estimate that to be about 20 to 25 degrees Celsius. Okay? And then the temperature in your body is body temperature, 98.6 Fahrenheit,
Yeah.
which is 37 degrees Celsius. Now which way is the heat going to move?
It's going to move from higher to lower, right?
So it goes from Mrs. Louis, look, all I have is your arms.
Yeah, that's
Your arms are not attached to you. There. Okay. So it's going to move from Mrs. Louis
higher
to the desk, to the lower temperature. Right. So we move from higher to low. And now let's talk about why, since the desk is the same temperature on top as it is on the bottom, why does the wooden part feel warmer and the cold part, the metal part feels colder? And here's why. The metal is a better conductor of heat.
Oh, yeah.
So it's not
wood, right?
Right, right. So it's not adding cold to your body. It's taking your body heat. See, there's all your body heat. It's taking your body heat away better than the wooden part on the top. So it feels colder. You see, there's not really such a thing as cold. You can add cold to something. But we can have the absence of heat, which we describe as cold.
Yeah.
Right, the absence of heat. So if we remove your heat, then you feel cold. And when you sweat, because you get hot, then the water in your sweat evaporates from your skin and takes your heat energy with it, so it cools you off.
Yeah.
And the same thing if you jump in a swimming pool on a hot day, and then you have the water absorbing your body heat, it feels nice and cool.
Yeah.
Yeah. That's what we always want. Okay, well, my artistic talents have been revealed. All of you can draw a better stick figure. I hope you draw better than I did. All right, so here's our important point. Heat moves from the warmer object to the cooler object, from high heat to low heat. And a better conductor is going to move the heat more efficiently. The wooden desk is a pretty good insulator. It's not a very good conductor. All right, and then here's how we calculate that. Q, which is heat, is going to be equal to the mass times the change in temperature. This symbol here means change. And then I left out this C here. The C stands for heat capacity. So we're going to change the temperature, and then C depends on what kind of stuff we have, whether it's a metal or what
Like
wood
a conductor?
or water.
Yeah.
Right. How good it is at moving heat and absorbing energy. The metal is better at that than the wood. You do that right. So let's describe heat first. Let's focus on just a chemical reaction which the system would need and describe to the chemical reaction, because that's where we're focusing our attention. So if we're looking at, say, there we go, H2O and CO2. And then office synthesis. Then we know we're going to make glucose. Well, and oxygen. Does that look familiar to you?
That looks familiar to me.
I sure hope so. We're going to need one more thing to make this work. This reaction is photosynthesis.
Yeah.
Yeah, our kids learned this last year in biology.
They're good at that.
Yeah, I think so too. So we need the sunlight to make this reaction go, right? So our system that we're focused on is this reaction right here. if we put energy in to this reaction, then we're going to make these products where energy is stored in the bonds in the glucose and in the oxygen. But we're not going to burn the oxygen, we're going to burn the glucose using it, right? When we eat plants and we get that energy back. Great, so that would be a system. We could also call, in our last example, the desk, your system, if we're focused on whether energy is moving to the desk. We could call you the system. But we would talk about only one system at a time. All right. So now, where do my... There's my... Now what? Oh, my writing's noise. Clearing that up. So we have this system is where we're focusing our attention. The surroundings is the entire rest of the universe. But we don't have to know what else is happening all throughout the entire universe. We just mean the surroundings is everything else but the system. Except the system. Yeah, right? And then the surroundings usually is what is surrounding your reaction. And so often it's water in the ether that is the surroundings. Yeah. And the chemicals that react are the system. So we don't want to confuse what happens to the water to what the system is. Because that's going to happen a lot in our class with reactions in water. Thermochemistry is the focus of heat that moves between the system and the surroundings. So we want to make sure that we know what our system is. Then the law of conservation of energy says that we cannot create or destroy energy. So during a change like this, whatever energy is lost by the system would be gained by the surroundings. The same amount of energy. Yeah. Because we can't have energy just disappearing into nowhere. Likewise, if the system gains energy, that means the surroundings lost the energy. Yeah. So we can transform energy from one type to another, like our students have learned about kinetic energy and potential energy. But we also can have heat energy. So we can change kinetic to heat, like by friction, right? Yeah. Q is energy. So if you're going to use a hammer, right? Yeah. Kinetic. Right. Gotta have it. We can also transfer energy from one substance to another, and that's just what we were talking about with your feet moving to the desk. Yeah. That's from one substance. So let's look at how heat moves from high to low, right? Yeah. So if it's going from, let's see, it says the system absorbs heat from the surroundings. From the surroundings means energy goes into the system. And so this prefix looks a lot like the word into. Yeah. It's endothermic. Where thermo refers to heat. And endo looks like into. Looks a lot like that word. So meaning the movement of heat on the surrounding into the system, right? To the system. Right. So what would happen then in the surroundings, since the energy moves into the system, its temperature goes down. But the temperature of the system goes up. Yeah. Right? Because it absorbs energy, right? And since the system absorbs energy, Q is positive because we define heat for the system. Yeah. So the sign for our calculation has to be a positive number for it to be endothermic. All right, now let's look at what happens if the system releases to the surroundings. Can you say now what is now? Yes, it is. This word will look a lot like exit, right? And so this will be exothermic. Because now the heat's moving out of the system into the surroundings. Right. So out of the system, where the system is our focus, it will exit the system. When it does, that increases the temperature of the surroundings. Yes. And the sign of Q will be negative. So in our calculations, if it's exothermic, we'll have a negative value for Q because the system lost it. Yeah. And when you lose things, then it's negative, right?
Yes.
Like if you lose money, your account balance is negative. I don't want to.
Oh yeah, I don't want that to happen.
Yeah, that would be sad. Okay, well I made a diagram to make sure that we get this. So here's my system in the blue, and energy is leaving the system. And here's our surroundings, everything else that's not inside the blue box. All right, so we know that, first of all, our change in energy for the system is less than 0, it's negative. Because the system is losing energy.
Yes, heat.
Like if I were to lose money, right?
Yeah.
So we're saying our change in energy for the system is less than 0. That's what we mean by negative. Not as in it's a sad thing, but
Yeah.
as in value is negative. We call this exothermic. Well, let's look at another example. Now, what if I change the arrow around?
Oh.
And the energy now,
From the surrounding into the system.
right, into, I think we know what that means. First of all, the change in energy for the system is positive. It's gaining more energy. That means it's greater than
0.
0. So, we call this energy. Our smart kids already know.
Oh.
Yeah. I don't have any kids that are not smart in my class.
Yeah.
So lucky.
Yeah.
I got the good kids this year. Well, you and I fight about who got the better kids.
Really?
I got the
I
I got the best. I trained them that way.
But I have good students in my class.
Yeah.
Don't ever take them away from me.
Yes, well, I've seen those students and how they work. They're pretty smart. Yeah. Yeah. Well, let's define units. How do we measure heat? Well, I gave you a hint. One of the ways that we measure heat is with this radiation, and you see it on your food label.
Oh, the calorie?
Yeah. Calorie defined by how much heat we need to raise the temperature of only 1 gram of water by 1 degree Celsius. So that's what a calorie is. But did you realize calories are not SI units? That's something that should be. Yeah, so we'll learn another one. It's easier to work with for other calculations.
Okay.
But a calorie, we're pretty familiar with.
Yes.
So if you guys look at your food and you see calorie on your food label, then that's a capital C calorie. This is a lowercase calorie.
Yeah.
There's a difference because the one with a capital C means kilocalories. And sometimes they're not very careful in your food label.
Yeah.
Right? They'll mix them up and put lowercase or uppercase either one. But always on a food label, they mean 1,000 calories.
Wow. So I need to be very careful.
Right. So if you eat a Snickers bar that has 250 calories in it, that's really kilocalories. We've got to add 3 more zeros.
Oh.
I love Snickers. That's one of my favorites. Students who bring me Snickers get extra points. I just want to make that clear on the podcast right now.
Just share it with me, okay?
Okay, you got it. You got it. The SI unit for heat is different. It's called a joule. And of course, it's named for a scientist who did a lot of experiments with heat. He did the same experiment over and over to make sure he got it right.
Yes.
And he did it over 1,000 times.
Wow.
I know. So he wanted to make sure he had it exactly right. So the SI unit for heat is called joules. And this is the amount of heat that's required to move 1 kilogram a distance of 1 meter with an acceleration of 1 meter per second squared. So we'll do a demonstration in class to show what that means. And I think Mr. Paycup is willing to help us with that demonstration.
All right.
So everybody, how much is 1 joule? All right. Here's our important conversion. It takes 4.184 joules to equal 1 calorie. So to raise the temperature of 1 gram of water by 1 degree Celsius, it's going to take 4.184 joules. That's how much energy. And
all right, guys, here we are to talk about units of heat for thermochemistry. Okay, Mrs. Hui, we did a podcast about units for heat. And we learned that 1 unit for heat is called a joule.
Yeah.
So here's what a joule is. It's where you lift the mass of 1 kilogram, which is a quarter pounder, 1 kilogram, for a distance of 1 meter. So if we go up to our mouths and back down, that's about 1 meter.
Okay.
And we have to move it with the acceleration of 1 meter per second squared. So we have to do it the same rate every time. And I just thought maybe we could burn off enough calories by lifting it. So we can afford to eat it, right? So we'll burn off the calories by lifting it, and then we can eat it.
All right.
All right, sound good? So ready? Let's do lift 4 times. Ready?
Ready? 1, 2, 3, 4.
Good, that's 1 calorie.
Yay.
Keep going. Ready?
All right. 1, 2.
Hey, wait a second. There's 4 joules per calorie, and there's 500 calories in that burger, which really are kilocalories, which means you have to lift it 2 million times to burn off those 500 calories.
Wait a second.
Oh, no. 2 million times, Dustin?
2 million times.
Really? I don't think I can live. I don't have that kind of
Too
time.
hungry for that.
Me too, I'm really hungry.
No, too hungry.
Maybe we should just go for a jog.
All right.
Okay, let's eat.
Yeah, that sounds good to me. And after this,
Thank you.